Good morning, guys. Welcome back to another episode of Introduction to Computer Networks. This is Polly streaming live again from NTU. So, good morning, Yin, Jia, Lucas, and Aslam. Okay, good to see you all. All right, so hey, you know what? Today we don't have anything special to announce, so we can go right ahead into the topics today. So today the topics are going to be in three groups. First is just to wrap up web cache. Remember yesterday we've introduced a particular example, and using that example we see through the basic setting. If you have a bottleneck link, the response time is going to be long, okay, because the queuing delay component can be high. So in scenario 2, you see that if we just expand the bottleneck link bandwidth, then the response time drops. Okay, but that solution there requires replacing cable and groundwork. That means labor cost. And nowadays, labor is a lot more expensive than the material. So it's a very expensive solution to try to bring the response time down. So in this scenario number 3 that's coming up, you will see that instead of expanding the bottleneck link capacity, all we need to do is to install a proxy server on the local subnet of all the clients sharing similar web objects, interested in similar web objects. Okay, so this video is a little long, about 7.5 minutes. There's a good reason for it, because the response time calculation for scenario 3 is a little bit complicated. In fact, the response time we're calculating is not the exact response time, it's the expected response time, because how long it is depends on the hit rate of trying to find a web object on the proxy server. Okay, so 7.5 minutes. The trickier part is to calculate the response time. In scenario 3, instead of blowing up the access link, let's install web cache here. I'm calling it the local web cache because we are very close to the clients. All right. Oh, and yeah, I meant local web cache here. Okay. So that you are not confused with the local cache we've talked about in conditional get, where that cache is actually very, very local on the hard disk of the user. So we are only slightly local here. So let's see. Good. So everything else stay the same. All we did is just install the machine. Now, if I ask you, changing this to 154 megabits per second versus adding a server machine, which one is more expensive? Yeah, you probably guessed, right? Labor costs, routers are expensive, cable sometimes can be expensive depending on the distance between the physical distance between the two routers. For your information, this could take millions of New Taiwan dollars. But installing a high-end server machines, it only takes this much New Taiwan dollars. So that's about 2 orders of magnitude difference. Yeah. Installing web cache, so much cheaper. Great. Now, let's see if the delay is also going to be better. Or maybe if this is cheaper, then delay is going to be worse. Now, let's try to calculate this. We know the LAN utilization, and so maybe the LAN delay is also about, microseconds. But access delay, well, we'll have to know the access link utilization in order to estimate the access delay. Therefore, question mark, therefore we couldn't quite yet estimate total delay, right? But then, so this has something to do with the traffic that needs to be brought down this way, right? How many objects will be coming down this way? That seems to be the question. And if you think about it a little bit more, isn't that depend on, for all these web requests we send to the proxy server, how many of them are going to be satisfied locally? Therefore, we could just, transmit the object from the web cache through the LAN to the clients without going all the way up to the servers. So that is this thing called the hit rate. Okay, amount of the proportion of the requests being satisfied locally, that's the hit rate or the success rate. Yeah, let's suppose the hit rate is 0.4. Then we see 40% of the requests will just stay here. Only 60% goes out and back. Great. So we know then the excess link here, the utilization is 60% of the excess link. 60% of the scenario 1. And how much is that? 60% of the traffic, then it's only this much traffic on the 1.45 megabits excess link, only 58%. So we cut the utilization from 99% to 58% if we ended up having this hit rate. Now let's calculate the total delay. So 60% of the time it's going to be long delay all the way to the server and back. 40% of the time just on the local LAN. Now, local LAN delay, we've seen earlier, microseconds, but I'm using the milliseconds here just to take into account the traffic here. So if we go out, request object down to the web cache, and then web cache serve the local client, we have one copy down here and another copy down this way. So the LAN here, the traffic potentially could also be higher. So let's use milliseconds just to be safe and take that extra traffic into account. Now, for the 60%, we'll have to go out and back, right? So this is very negligible. This part is what? The key component. This part, 2 seconds, we know for sure. So what's remaining is just the delay here on the excess link with 58% utilization. Well, how much delay is this? If there's a lot of queuing delay, we go minutes. If very, very low, only 1%, we go milliseconds. So minutes, milliseconds, well, that's, saying tens milliseconds or hundreds milliseconds, right? So I'm trying to be a bit generous here and use 10 milliseconds only. And so total delay here about 2.01. And 60% of that plus 40% of milliseconds. The dominating component is the 2 seconds. So you see here, the overall total delay on average is going to be about 1.2 something seconds. Is this better than scenario 2? It is, right? Scenario 2, you have at least 2 seconds. So what's amazing about web caching is this. The benefit is not just that it's cheaper, but the delay is also lower. And the traffic coming down this way is also lower. Hey, we did not spend any money here, and we also saved some bandwidth here as compared to scenario 1. So there's more traffic can come down this way. Isn't it nice? And that explains why we need web caching, right? It's to reduce the delay. This is also called the response time, okay? That meant the time it takes to issue the request all the way to the server and bringing down the web object. The round-trip delay of the request and response messages. It also reduces traffic, save a lot of bandwidth on the access link, and it's very cheap. Now, an extra benefit we didn't talk about is because we did not assume the uplink bandwidth of the servers being the bottleneck. If the server is poor, meaning having a poor content providers out there, then, let's say that the server here is poor. It cannot afford too high bandwidth uplink. Then reducing the amount of traffic going this way also saves poor content providers some resource, some money. And so web caching there also help the poor content providers to deliver content, all right? And this could be a good thing because most of the NGOs, they might also have information to disseminate, but they couldn't provide good uplink bandwidth. And that actually gives rise also P2P file sharing. The idea of P2P file sharing is also, hey, if I have the copy of the content and another peer grab a copy of it, then this other peer can help serving the other peers. So that peer there is working pretty much like a web cache, isn't it? Like a proxy server. So you could actually think of a P2P network, a network of these proxy servers. Okay. And you saw a bit already. Next slide. Coming next is going to be the second application in chapter 2. And we'll look at how FTP defines its application layer protocol. All right, so let's exercise critical thinking a little bit. All right, with the web cache, you see that the response time is going to be lower, the traffic volume is going to be lower, and you see now with the example, three scenarios, it's a more economical solution. But do you see potential issues there? So think, what if the hit rate is low? Isn't it? In fact, in the third scenario, what we're calculating is the average response time. What about the worst case response time? Are those better if you compare that to the second scenario, right? So second scenario, very expensive, but the worst case response time or best case response time, all of them are lower. But the third solution, it's more economical. The average response time is better, but it's not necessarily, the worst case response time is not necessarily better. Okay, good. So web cache, it's a very nice alternative to try to bring up the efficiency of web transfer. Now, that's the first topic. The second topic is to introduce the second application called email. And this is an application you will see the first time that requires multiple protocols, okay, in order for it to work. So the first set of video talks about the architecture communication model. So the first of the first video sets is to introduce the basic components. There are three: user agent, the mail server, and the protocol running between the user agent, aka the client, and the mail server. Okay. In the later half of the video, you will see also an example. Okay, Polly explains step by step when there's someone sending an email, how these components mentioned would pass the emails from one to another component. Okay, so first video. 2.3. Emails. So this application is a little bit unusual. It's supported by not only one application layer protocol, but multiple ones. And we'll talk about it more. Email application. It's got three major components. First is the user agent. This is the software running on the machine closer to the users. And mail servers are the software running on more resourceful machines farther away from the users. And among these mail servers, it runs this protocol, SMTP, the Simple Mail Transfer Protocol. These we'll also talk a bit more about. Let's start from the user agent. They're essentially the email readers. They allow us to write email, edit email, read emails. Outlook from Microsoft is one mail reader that's very well known. Thunderbird. I don't know if you know about this one. This is from Mozilla. So the company that produces also Firefox, the very well-known web browser. iPhone comes with a built-in mail reader. Google is also trying to push for a Gmail mail reader. So there are so many of these email readers these days. Now, keep in mind though, the actual emails are all stored on the servers, not on the user agent these days. All right. Now the mail servers. It's got these three major components. The mailbox, which contains all the incoming messages per user. So these are the yellow boxes. When emails come in, they will be sorted out and then put into the email boxes depending on who the receivers are. Second component, the message queue. Those are the green queue over here. So messages that are going out will all be stored here temporarily and waiting for the receiving mail server to open up and then accepting the emails. So SMTP protocol there is to allow the sending server and the receiving server to communicate. Now here in particular, the sending server there is called the client of the SMTP protocol. And the receiving server is, on the other hand, the server of the SMTP protocol. So you see a little bit here. The SMTP protocol is to provide mail receiving service in a sense. So client here requesting service, server here allowing emails to come in. If you think about it more, it's got two levels of communications in the email application. So this is one between the end users and the local mail server. Okay, fetching email or pushing email out. But there's another level, which is among the mail servers. All right, so sending mail server is the client of the higher level communication. Receiving mail server is the server of the higher level communication. Then the SMTP protocol. So this is the actual application layer protocol defined to support communication in emails. So let's see, what are the underlying protocols and what is the communication model and what are the messages defined? TCP you see here. Therefore, SMTP is to support reliable email receiving service. It runs on port 25 and the transfer is direct between the sending and the receiving server. The exchange, very simplistic, 3 phases, handshaking, and then extra transferring of the emails, and then closing. Opening, closing, the extra transferring of the emails in between. The messages are also simplistic. They're just comments coming from the sending server, responses coming from the receiving servers. So comments in ASCII code, just like HTTP, just like FTP. Responses, status words, status phrases, status code, just like HTTP and FTP. They all run in the ASCII code. Now put all 3 major components together and let me illustrate with a concrete scenario. Alice here is sending an email to Bob over there. All right, so Alice will need to start the user agent first to compose an email. So in the email, it will need to specify the receiver. And then the user agent will send the email to the message queue, okay, in the local mail server. So that is step 2, emails going to the message queue. And then the client side of the SMTP, which is here, this guy is the one sending, and this Bob's mail server will be the one receiving. So this is the client of SMTP. This is the server of the SMTP. So client side of SMTP will open up a TC connection. Once the server is allowing the connection, then the client can begin sending Alice's email. So that email will travel, and the server here of Bob's will check whether the receiver is Bob, and therefore putting the email into Bob's mailbox. Right? So email goes to Bob's mailbox. Lastly, when Bob now joins the internet, invoke his user agent, then the agent already pre-configured to connect to the incoming mail server will then fetch the mail messages, and that's when Bob gets to read the email. All right, so in this video, make sure that you remember this. In SMTP, the sending mail server is the client. The receiving mail server is the server. Okay, so this is a little bit different from the HTTP protocol, isn't it? In HTTP protocol, the machine sending the web object is the server. Receiving the web object is the client. Okay. So the role of the server and the client depends on the service, really, not depends on the direction of where the real data is being transmitted. So in SMTP, the sending one is the client, receiving one is the server. Another thing that you wanna notice also in that video is, hey, receiver is Bob. Okay, in the whole process, we say that, hey, in the end, in order for Bob to really read the email, Bob needs to invoke the mail reader and fetch the emails from Bob's email server. So it's unlike when the sender is trying to send email, all the user agent needs to do is just to send it directly to Alice's mail server. So Bob's, so at the receiver end, okay, it's a little bit more active. Okay, one needs to go find the email, go fetch the email in order to read. But at the sender side, sender is it's okay to be passive. Email done, hit send. The mail will be automatically sent by the UA. Okay, so there's something that you want to pay attention to. Next video here is to show you an example of how the client and server exchange messages. In the video we just played, we know that it's very much like HTTP. The messages are readable ASCII text. So in this video, you will see the exchange of these ASCII tags. And towards the end, you see Polly trying to demo, just like Polly did for HTTP. Pretend to be a client and try to interact with the mail server. All right, so this is the video. This is a very simple SMTP exchange. Let me explain the notation. S being the server, C here being the client. Now in SMTP, this is the receiving mail server, and this is the sending mail server. Once the TCP connection is established, the receiving side identifies itself first. 220 hamburger IDU, status code, status phrase. Client here then would in turn tries to identify itself as well. Crepus.friends, that's the identity. And hello here is the command to allow the server to know who the client is. And then server, status code 250, everything is fine. Hello, crepus.friends. And then beginning from here, we start to see control message exchange. Client here needs to specify who the sender is and who the recipient is. So mail sender is Alice and mail recipient is Bob. So all capital here, mail from. All capital here, receive to. Okay, our special commands as well, just like the hello. So whatever comes after the columns are the mailer and the recipient. So server again are just saying, okay, good, I got it, 250. And from here on, this is the actual data exchange. Data, once again, a command. Email starts from here. Do you like ketchup? How about pickles? And it ends with a single line that has only a period. Okay, so the actual email message is only this short, 2 lines. Last is here, just to close. Okay, server will say, message accepted, everything is fine. Client then issue yet another command to quit the session. Server says, all right, goodbye. Very simple. To set up connection, to do the email exchange, and to close the connection. In the email exchange, there's the control message part and then the actual data part. And that is an SMTP message exchange among the client and servers. Let's try now to telnet to an actual mail server at port 25 and see what the server would send back to us. And then we could try to typing some of these comments out and see how the server responds. So let's go to the demo mode. Now let's try telnet to a mail server at port 25. Telnet, which mail server? Actually Googled up Gmail's mail server. The name is this, SMTP, how appropriate, gmail.com, 425. There we go. IP address being 64 something something. And this is a message coming from the server, 220. All right, so SMTP, gmail.com there is identifying itself. And then ESMTP, okay, it's saying more. I'm not quite sure what this is, right? So E must be something and then SMTP. So this might be a special variation of SMTP, maybe the encrypted version, I'm guessing. So let's try typing up some of the comments. For example, hello, and coming from us.edu.tw. How about that? Great, it seems to be working. 250. So the server is saying, ooh, at your service. That's really polite. All right. Then let's try the next comment we saw earlier, mail to. And let's have Gmail sending to pollys email address. How about that? What is this? 530 5.7.0 must issue a start TLS comment first. So yeah, it does look like it's trying to establish an encrypted connection. So TLS, if you recall, is what? Transport layer security support. So I'm guessing this is probably the credential, the public key. So I'm supposed to send back the shared secret key with the public key as the key to encrypt. But I don't know how to do that. So yeah, let me try it again then. Playing dumb here. Polyhuang at ntu.edu.tw. Let's see. No, it's not accepting it. So I have to, yeah, so maybe recipient from, Polly's Gmail address. How about that? No, it keeps bugging me saying, okay, let's do start TLS. So that's issue this comment, start TLS, and see, start TLS. Oh, cool, it's accepting. That's nice. Ready to start TOS. All right, so then I suppose I need to send back the, uh-oh, I'm already out. So it seems that the establishment process there also has a time limitation. Otherwise, yes, and hacker might be able to hijack something that you have done in the middle. Interesting. So, hey, I got kicked out. So Gmail is a secure email service. Email messages are encrypted. Nice. Good to know. And so that was a demo of trying to telnet to a mail server, actual mail server. You could also try this yourself, maybe from the workstation. Okay. All right. So that was SMTP. As August was commenting that SMTP is all these days, all the mail servers are running eSMTP, the secure version that's running on top of TLS. Okay, so that's why you see in the demo, Polly has trouble connecting to Gmail's mail server because it's running eSMTP. All right. By the way, Polly was also a little bit mistaken trying to type mail2 to send the to indicate that it's an email coming from Polly Huang at ntu.edu.tw. It should be mail from, not mail to. Similarly, for receive from, it should be receive to. All right. Good. So that was a communication model. This is so these two videos are to give you a general idea how emails are sent. Next video, we'll talk a little bit more about the messages. As you heard in the earlier video that it's email also uses ASCII readable text. Okay, so there's a certain format in it. In fact, in this video, you will also see that we try to compare SMTP to HTTP a little bit more. So message formats and comparison to HTTP. And just a few words about SMTP at the end. Once it sets up a TCP connection, the client there can use the connection to send multiple emails. So it runs just like the persistent connection we see in HTTP. SMTP requires text in ASCII code, very strict. And SMTP uses just a single dot in the last line, okay, to determine whether it's the end of the message. Now, if we compare SMTP to HTTP a bit more, they differ in multiple ways, but they are also similar in another way. So this is the first thing they're different. Yeah, the service sort of direction. HTTP is actually to pull objects down, but SMTP is to push objects out. Now, object here, I meant email. They are similar in this way. Comments, responses, all these messages are in ASCII text format. But HTTP and SMTP are also slightly different in this way. Each object is encapsulated in a response message. So HTTP server there sends one object at a time, one object per message. But SMTP can send multiple objects in one message. That message is just having multiple parts. So for emails, that comes with an attachment, like a big PDF file after, here is the attachment, if there's anything wrong, contact me. So email, the original text at the beginning, and then additional attachments. They can be sent as a multi-part message. So multiple objects in one message versus HTTP. One object, one message. Mail message format. So there's yet another protocol that defines how the email messages should look like. So this will be the data part of the SMTP protocol message exchange. If you recall in the example earlier, there's the opening phase, some control messages being sent, and then comes the actual data before closing. So the mail messages here we're talking about is the content being sent in the data phase. All right, so these messages are not control messages for SMTP. So they are not SMTP. The mail message format is actually defined in another RFC. It's another protocol. So in that protocol, it defines the mail message format. There are two parts only. The header containing a number of header lines, specifying who the receiver is, who the sender is, and what is the subject of the communication. In the body, very simple, just the content of the communication. So note again that I tried to clarify. In SMTP, you see mail from. So this sounds like, following this command, you also tell who the sender is. Receive to, after the column,
you give the recipient's email address. So it sounds a little bit like the to line in the header line and the from line in the header line, but they are actually completely different things. These go in the data part, while these go earlier, setting up a connection ready for data exchange.
All right, so those are the messages. And by the way, I said that the mail content itself has got a format. Okay, that is very unique. If you recall in HTTP response, we have the status line, we had the header lines, an empty line, and then the data. There's no specific format required for the data part, but in email, okay, that email content itself, there's a format for it. Okay, so that is the last part of the video is about. Okay, all right, and we move on to the last segment of the entire email transfer. That is between the reader and the reader's server. Okay, and that is called email access protocol.
And then we'll switch gear just a little bit and talk about the last part of email application. So we've talked about the flow of sending an email all the way from Alice to Bob, right? So mail access protocol runs here. Okay, so it's this part of the entire flow. SMTP that we talked about earlier only covers email exchange to the receiver's mail server. In between the receiver's mail server and the actual receiver, it's this protocol that's controlling. So what it does is to allow the receiver to retrieve email from its local server. There are three very popular mail access protocol: POP3, Post Office Protocol, IMAP, Internet Mail Access Protocol, and HTTP. These two, you can see that they are more specifically defined for the purpose, allowing a receiver to retrieve email. The functionality is also similar. First, the receiver needs to authenticate itself, authorize itself, and then begin downloading emails. IMAP, being a slightly newer version, okay, it includes a number of other features, including, for example, we could store the email messages in a more structural way, for example, creating folders and putting certain emails in certain folders. Right. HTTP, however, is special. It's quite fashionable these days. Some of the mail service providers are asking us to use a web browser as the user agent. And then the email server there is essentially also a web server, so that it runs HTTP in the middle and treating each email as a web object. So fetching an email, fetching a web object. Okay, it's the same thing, except that the content is more specifically being emails. And let's take a closer look at how POP3 works. Okay, the exchanges between the client and the server. The notation is very similar to the exchange we saw earlier in SMTP. S being the server, client is C. So there's an authorization phase and then the actual transaction phase. So authorization phase you see here, the client comments very typically being declaring the username and declaring the password. So you see here, in the authorization phase, the server says, okay, I'm ready. Client says, I'm user Bob. So the username there is Bob. Password, being hungry. All right. And server responses with either okay or negative error. It's even more simpler. All right. So okay here, okay here, okay here. Maybe with the phrase after that. And in transaction phase, this is where the emails are actually retrieved. So clients sometimes say this, list. So this is to ask the servers to tell back the list of emails there are. So this is more the index of the emails, and a lot of times just containing the file size and maybe the subject line. Right? It's only until the client begin issuing comment like this, RETR. So this is for retrieving messages. So RETR1 indicates that it's retrieving this email. So this is the index of the email, the size of the email, and there could be other information. Then the server sends back the actual content of the first email, and again ends with a period, and only one period in the whole sentence. Right? The client can actually delete an email that has already been read, or in case it's a spam. Right? So DELE, very intuitive, being the delete. Quit, also intuitive, being quitting the session. All right? So retrieve an email, server sends an email, client delete an email, retrieve another email, server sends another email, and client deletes yet another email. Q and then plus OK, server says goodbye. So that's an example of POP3 exchange.
All right, so the second half of the video is essentially to show you POP3 protocols, the messages and comments being sent. So once again, in ASCII readable text. And also, with that video done, it's time for a quiz. So this is quiz 12. Let me move to the whiteboard mode so I can dribble. So, hey, you've seen, right? So the flow of emails from the sending user to the receiving user is this. User agent, the sending side, generates email, hits send. That email gets to the sender side of SMTP, right? And then SMTP will send that email further to the receiver side of SMTP server. And finally, Bob will need to invoke, okay, the mail access protocol to fetch mails from the wait queue, okay, to the user, the reading user agent. Okay. Now, so you see, okay, up to receiver's mail server, it's all SMTP push. Okay, so this is a push protocol, unlike HTTP, a pull protocol. Okay. Why can SMTP just keep pushing to the reader's user agent? Why not SMTP all the way to Bob's user agent? All right. So guys, this one might be a little bit tricky. For some of you, it might take a little bit more time to think. So let's go to Discord. Channel W5, quiz 12, oops, A. Okay, so let me upload it again. So guys, this one might take a little bit of time. So you guys have 7 minutes. So gather your teammates, discuss, and 1 minute to type your answer. So Polly will not be taking fast responders, so take your time. Polly will be taking thoughtful responses this time for extra credit. All right, so why don't we start counting time? 7 minutes, thinking, 1 minute, typing up solution. All right, time's up. Let's check out what you guys have to say. Okay, wow, Team 1 is expanding the list of reasons that SMTP will not work, going all the way to the receiver. But I guess the first reason is the most commonly seen. Server is more reliable. Client PCs don't have high availability, and this is crucial for receiver. Yeah, you see, in SMTP, the receiver side is the server. The receiver is expected to be on 24/7. And you know what? If we do that, okay, let me remove all the markups first. Now, between receiver's mail server and Bob's user agent, if we need to run SMTP, obviously, this needs to act like a SMTP server, which means Bob needs to be reachable 24/7, right? But Bob is what? A user moving around. So, very good. Team 1. Yeah, so one obvious reason is that to be the receiving end of SMTP, the receiving end needs to be reachable all the time. And a client PC where the receiving user agent is not really available all the time. For example, if the client is connected through NAT, an AT, the network address translation service. So even though the user is up and working and typing emails, but that user agent is still not reachable for the sending SMTP server. Okay. Now there are a few more reasons. Let's see. Reduce spam. Yeah, I think this is also a reason that growingly important. So even if we have a user agent that's running on global IP address that's not behind NAT, okay, it will still be nice, okay, better to have a server there, okay, doing authentication of the messages, right? And if just a user agent, receiver's user agent, it's a little bit hard to install such a function. Okay, so yeah, there are some existing protocols and tools that allow us to check the authenticity of the mails. Whether the sending email address exists, whether the sending email comes from the mail services they claim, the sending email address claim. Simplicity, oh cool. We don't want to run a whole set of email handling on every single PC. I see, this is a very interesting argument, August, or Team 1. Yeah, so this is trying to keep the client. Yeah, it's probably my laptop. It could be my smartphone, right? So these are machines that are limited in capacity compared to the servers. Yeah, so we could move all these expensive or computationally intensive functions or storage intensive functions to a server. Storage limit, exactly. Yeah, so 3 and 4, I think this is falling in the line that you offload computational expensive, storage expensive functions that will be nice to have or important to have these days into other machines. And so keep the user agent simple. As a result, the user agent needs to invoke the email reading process actively using a mail access protocol. All right? Yeah, so yeah, Clara, Team 15 here says, okay, very well explained. Yeah, Bob, the user agent will need to pull the message from the server. And SMTP is, if we use SMTP, Bob's user agent will need to pull the emails. Okay, and so Bob is going to be a server. And Bob cannot be there all the time, right? All the way to the server, the user agent computer needs to be ready to receive. I think the similar argument as Team 15. And I think this is also what Team 1 meant here, right? So server there needs to be there all the time to receive the emails. I think, similar here. To transmit message from client side to the server side. Yeah, this is perfect. Okay. Wow, okay, very supporting teammates you have there. Okay, good for you, Team 7. And Jiaxun. Yeah, so Jiaxun's argument is similar to the second reason from Team 1, right? Yeah, so you might want to reject some of the messages, okay? And it's better to have this function at a server instead of the user agent. And so it's better to leave the emails at the receiving server for a while and wait until the user agent to fetch the legit emails later. Okay. All right. Yeah, I think this is enough walkthrough. I think you guys get the idea. Avoid spam. Able to interact with the servers. Allow email provider to have more flexibility. Good. Instead of pushing the... Oh, okay. I think for Team 17, yeah, so you're describing that SMTP works only to the receiver mail server. And for the Bob's user agent, it would currently, it's defined such that we use a mail access protocol to fetch emails. So the question, the quiz here is asking, why using a mail access protocol? Okay, why it's designed this way? Okay, so that's why I'm asking you again, why it's necessary for the user agent, right, to use a mail access protocol. All right, I think you guys are probably pushing, yeah. In SMTP, we push the message automatically to the receiver end, right? And so user agent this time is pulling the mails, therefore an access protocol. Requires the receiving device to be always running. Perfect. Yeah. Good. And guys, you know what? It's 11:12. Polly is going to read through all you guys' solution. And in case I'm looking for more, then I'll let you know. Okay. So, and this is also time to take a break. So as Polly is going through all your solutions, let's take a break. It's 11:13 now, and we'll resume the lecture 11:23. Okay, break. All right, so that was email. It's more complicated than HTTP, obviously. All right. Now, the last part, the last set of topics is going to be the third application called DNS, Domain Name Service. The first video is to introduce exactly what DNS does.
Next is chapter 2.4 DNS, which stands for Domain Name System. And before we talk about the purpose of it, let's talk about identifying a person. If I tell you my social security number, my name, and my passport number, which one would you think would be easier to memorize? Well, social security number, 10 digits long. Well, the national ID of Taiwan is also about 10 digits long. You can correct me if I'm wrong. Name, Polly Huang. Passport number, don't even bring this up. Polly does not recall her passport number, as a matter of fact. So very obvious, isn't it? The name is so much easier. Well, that's just how human brain works. Name, form of ID, much easier. Number, form of IDs, harder, especially when it's a long sequence of numbers. Well, internet, to identify a machine on the internet, shows a similar obstacle. So hosts and routers, many of them have the IP addresses, right? But these IP addresses are even harder to memorize, maybe harder than the passports. And as you're working on the PAs, right, memorizing the IP address of the workstation, super hard. Even though you've already worked on it for a while, if I ask you to type it up, it's probably still challenging. So what we do here on the internet is to give some of the important machines also a name. For example, www.yahoo.com here is the web server of yahoo.com. So you could just type www.yahoo.com and it quickly leads you to Yahoo's website. Similarly, www.google.com, quickly we reach Google. So, hey, how does the web browser know? What is the IP address of the web browser given just www.yahoo.com? Well, that is the functionality of DNS, to identify the mapping between the IP address and the name. And let's talk about DNS more formally. So essentially, it's a database of these mappings. So lots of these IP address mapping entries. Nowadays, it's distributed, meaning there are multiple of these name servers, and there's a hierarchy actually connecting these name servers. Some of them sitting at the higher hierarchy, and some of them sitting lower. What's a bit special about DNS here is if you hear me saying that, hey, a web service will need to query DNS system in order to find the mapping. So, hey, web service is already an application level service. HTTP is already the application layer protocol. So it seems that the application layer protocol, HTTP, there needs to work with DNS, which is also an application layer protocol, in order for it to operate correctly. So DNS, in fact, work with multiple of these application layer protocols, not just HTTP, all right? So name servers there would help all these application layer protocols in order to resolve names to the IP addresses. It's a very essential function. Some might argue that it's one of the core internet functions, which might sit underneath the application layer protocols instead. But now we put it in the application layer such that it's only running on the end hosts. If we need to update, improve the DNS servers, we don't need to actually go ahead into the core of the internet, all these routers to change everything. So that makes changes a bit easier. Right? So there's a very special phrase that the internet designer would like to say, which is complexity at the network's edge. What it means that if you come up with something, some function that's very essential and it could go complex, then let's put it at the edges. Let's have it running on the hosts instead of running in the routers at the core of the internet. Okay. And a good side of doing this is so that we could evolve quickly and the performance bottlenecks can be removed quickly. Right.
All right, so basically, DNS is to provide these mappings from the host names to the IP addresses. Just like August, I don't know what your social security number is, so it's obviously easier for me to memorize just August Young instead of a series of 9 numbers. Okay. Okay. Jane Guy is saying something. Well, I'll come back to that. And hey, complexity at the edge. So if you recall, IP addresses are important for the core of the internet to know, right? When a packet is received, which way to forward next. Okay, so passing these packets around is actually a lower layer, a network layer function. Okay, so mapping from the host name to the IP, therefore, is actually more related to this, how you forward packets. Okay, so if we do DNS, do the translation at a higher layer, for example, application layer, this is to try to push complexity that is supposed to be in the core of the internet to the edge. And as you heard, there's a good reason for that, because these functions that are important and it might grow to a large scale service, then it's better to push them to the edge and keep the functions in the routers simple. Okay, so that is why DNS, seemingly a lower level function, it's however implemented and running at the application layer. Okay. So it's a little bit controversial to call whether DNS is an application layer function or a network layer function. In terms of the purpose of the function, it's network layer. But in terms of the implementation, it's at the application layer. Okay, good. Oh, we have also some guest students. Okay, good morning. Now, let's play the second video. You see, DNS is to provide the host name to IP address mapping. But you know what? This is not the only kind of mapping it provides. There are actually 4 types of mappings DNS provides. So this is what the next video is about.
DNS services. There are multiple services actually DNS provides. First is what we've talked about, the most basic one, from the host name to IP address translation. It does 3 other forms of translation. First is the host aliasing. So what happened often on the internet is that some hosts came with host names, but the host names could be slightly longer, indicating where it is or which one of it, number 1, number 2, number 3. Okay, so those can still be slightly harder for users to memorize. So alias name here is often cute and short, and very easy to memorize. So this is where the users know the services are, such as www.google.com. All right. So from alias name, DNS allow the web browser to look up what is the canonical name of the server, and from the canonical name of the server, identify the IP address through one of these mappings from host name to IP addresses. So that's how host aliasing works. Second, mail server aliasing, right? So I mean, you must have one of these, right? Gmail accounts. If your friend is sending email to your Gmail account, your friend's mail server will need to know who's your mail server. So who's Gmail's mail server? This thing actually looks very general. It's in fact a domain name, not quite a host name. So what happened in DNS is there are also these entries saying for this domain, gmail.com. Okay, all the emails destined to this domain should send to this machine, SMTP, gmail.com. This we talked about when we were telnetting to an email server to demonstrate the message exchange there. smtp.gmail.com is the actual mail server for gmail.com. So there are also this entry here in DNS service. Okay, and this is called the mail server aliasing service. Last, okay, this one is a bit tricky, but it's growingly popular. It's called the low distribution service. What it does is this: for a host name, there could be multiple IPs that map to it. So IP1, and then the same host name, IP2, IP3, IP4, and so on and so forth. Okay, what happened here is that the DNS might actually rotate, returning different IP addresses each time a web browser or an email server looks up for an entry, okay, for the particular host name's IP address. So that way you kind of rotate using different physical machines every time, and therefore distribute the load of the service. Why not centralize DNS? You heard in the previous slides, there are multiple name servers and there's a certain hierarchy behind it. So why not just one? Well, it doesn't take long. At the beginning of the internet, there's indeed just one DNS server, but it doesn't take long that we realize when the machine is off, the entire DNS service is off. And everyone on the internet, unless you can memorize the IP addresses of all these servers, otherwise, there's not much you can do. Okay, it's off. Second, every application that needs to find mapping IP address given the name, traffic needs to go there. So very high volume. It gets really busy at times. And hey, those users that are around this particular server will have short delay, but they will always be part of the world far away from a particular machine. So delay not ideal. Some could suffer forever. And maintenance, this is a tricky issue, but it is indeed a problem. There are two perspectives looking at the maintenance issue. One is that the DNS server software is growingly large. When it grows too large, if you want to make just a tiny little change, you need to what? Turn off the machine, update the code until you can put it back running, right? But all you want to do is just to make a small change. So one small change influences the entire internet. Not good. Second, it's also hard to do the maintenance, right? Because if you want to just do some testing, debugging, you have to take down the entire DNS as well. And when the software grows large, chances higher that you need to do the testing longer, debugging longer. Not good either.
Yeah, this is why in the next video you will see in DNS, there's not just one server, there's a hierarchy of servers. Okay, so this is what the video is about.
Therefore, DNS is not a centralized system, but rather a distributed hierarchical system. And this is how the hierarchy looks like. At the top, the root DNS servers. Second level, the .com, .org, .edu DNS servers. The lowest level, or the authoritative server level, the yahoo.com, amazon.com, pbs.org, poly.edu, umass.edu. So what you're seeing here is, hey, .com further breaks up the namespace, and each of these server at the bottom will serve a small range of the names there are on the internet, right? So distributing the load of the name IP lookup. Now, the process of looking up the IP address in a nutshell is this. Client now wants to get the IP address of, for example, www.amazon.com. What it does is first query the top server and try to find the second level server. Query the second level server, next try to find the authoritative name server, the last level. And then from the last level of DNS servers, finding the IP address for a particular host. And let's talk about each of these name servers a bit more. At the top level, the root name servers. It's connected by the local name server. Now allow me to explain. This local name server is not in the hierarchy. This local name server is actually very, very close to the client. Typically what happens is that a whole bunch of these end hosts sitting in an ISP will be sharing one. So ISP or institutional network will set up a local name server there for all the users in the domain to send the queries. And then this local name server then will relay the queries to all these servers in the hierarchy, right? So in a way, the local name server here is the client of the name to IP lookup service. So a local name server contacts the root server first, right? The root server then will contact the authoritative name server to find the mapping, get the mapping, and then return mapping to the local name server. Now, the trick part is this. When I say contact authoritative name server, it's not like directly going from the root to the authoritative name server. There's a certain way of rerouting the query until it reaches the authoritative name server. Authoritative name server is really the one containing the name and IP mapping. Okay, the top level knows the second level. Second level knows the authoritative servers. Only the authoritative name servers knows the exact mapping. And you see here, there are not many root servers. There are 13 logical root name servers, but each root name servers now have multiple physical sites. For example, here in Tokyo, there are 5 sites, 37 sites just for the Swedish root server, etc. So there are quite a few in America, but essentially very few of these root name servers. Next, the second and the third level DNS servers. At the second level, we have a bunch of these TLD servers, top-level domain servers. They're responsible each for a different top-level domains. So top-level country domains as well, UK, FR, CA, etc. So essentially, this is the last part of the host name there. Right? And each of these TLD server is maintained by some sort of organization of public interest. Some people call them NGO. So for example, Network Solutions maintain the servers for the .com TLD server and EduCost for the .edu TLD. At the third level, we have these authoritative DNS servers, right? So it maintains the IP host mappings. And it could be maintained by the organization itself or by a service provider if the organization is somewhat small and there are not many entries reading. Local DNS server, this I tried to introduce earlier. It does not belong to the hierarchy, 3 levels. It's very special. Each ISP or institution network will set up one, and all the clients in the institution or in the ISP will configure themselves to send all the queries to this local DNS server, which is also called the default name server. So when a host makes a DNS query is always sent to the local DNS server. These DNS servers often carry these caches of recent translation. So whenever we get a host to IP address mapping to the local DNS server, of course, forward the answer back to the client. But in the meantime, the local DNS server also keep a copy of that, okay, for some time. And this is for the benefit that if the client is looking for the same name again, okay, same name IP mapping again, then it's conveniently already cached in the local DNS server, avoiding going all the way to the hierarchy. So nice. But be careful. These entries could sometimes go out of date. So while these entries are cached locally on the local DNS server, well, the entry might have been changed in the authoritative DNS servers. Okay, although very rare, but there's a chance. So these local DNS servers, if you think about it, it works more like a proxy server. Okay, it's not exactly client, it's not exactly server. It's something in the middle, helping relaying the queries, relaying the answers. Helping forward queries into the hierarchy if there's no hit here at the cache.
All right, so root DNS server, top-level domain DNS server, authoritative DNS server. And then there's also a local DNS server closer to the clients asking for the mappings. Okay, so that's the hierarchy of the servers. Next video shows, in case now you have a mapping you're looking for, how the queries are forwarded through the hierarchy and eventually gets a reply, meaning having the exact mapping that the client is looking for.
So far, we've learned that there's a hierarchy in the DNS servers. There's the top, second, and the third level. And we also know that there's a proxy server. They're always working on behalf of the client, sending the DNS queries. So let's try to explain further from the local server here how the query is forwarded, okay, and eventually receiving a reply. And let's do that through an example. Okay, there's going to be a host trying to reach Gaia.cs, but before messages can go out, CIS poly here needs to find the IP address of Gaia.cs over there. And we're going to illustrate this form of query forwarding. It's called the iterated querying. All right. So what the local DNS server does is to contact the server in the hierarchy, and the server will reply with something like this: name of the server to contact. Okay, someone who might know a little bit better, but I don't have it. So messages looks like this. Root server might say, hey, I don't know about Gaia.cs.umass.edu in particular, but you may ask, hey, the top level domain server for .edu. Okay, someone knows slightly better than I do. Okay, but I do know someone who knows better. Right? So that's the general idea. And so the process goes: client here issuing query. Local DNS server now forwards the query first to the root. Root returns the IP address of the .edu TLD server. Therefore, the local DNS server could re-forward the query to .edu TLD DNS. Top DLD DNS does not know the IP just yet, but top level domain DNS does know the IP address of the authoritative DNS server, so that will be sent back. And the local DNS server sends the query the third time, okay, to finally the authoritative DNS server. And finally, the IP address for Gaia.cs comes back to the local DNS server. Local DNS server forward that back to the requesting client and be happy about it. Recursive query is the second form of doing the querying. So local DNS server here will forward only to the root, okay, and not contacting DLD, not contacting the authoritative DNS server. And it will be the root's job to find out what the mapping is. And root doesn't really know the mapping of Gaia.cs.umass.edu. So he forwards the query to TLD. TLD forwards to authoritative DNS server, and finally the IP address traversed back. And root DNS server here sends back to the local DNS server. Right? Can you see an issue with this? Yeah, so this way of querying puts burden on named servers that's high up in the hierarchy. There's going to be a lot of query comes to the root, and there's going to be a lot of queries coming from the root to the TLD, although the load on the authoritative DNS server remains the same. Right? So heavy load at the upper level of hierarchies, not good. Keep in mind, there are only some tens of root DNS servers, physical root DNS servers. If everyone is sending the queries always to the root, we could quickly bring down all these root DNS servers. And that's not really a viable solution. Therefore, recursive query is an option that we try to disable at the local DNS server.
All right, so that's a hierarchy of DNS server system and how you go through these servers to eventually find the mapping. So there are two modes, right? Iterative and recursive. I guess most of you like the iterative ones, but maybe let's take a poll. Okay, guys? If you prefer the iterative query, say iterative. If you prefer the recursive query, says recursive. Okay, on the chat, please. And in the meantime, you're trying to type things up. Let's move to quiz 13. Recursive, August. Okay, very interesting. You don't mind whether the root server is bombarded by requests, I guess. Okay, I guess that's because of the confidence operating the K-root, right, server. Okay. Hey, there are a few more also like recursive query as well. Yeah, and I guess slightly more of you prefer iterative, right? Okay, there seem to be more recursive query preferences. Okay, very interesting, very interesting. And guys, maybe you can also tell each other why you prefer recursive over iterative or vice versa. Okay, now when you guys are typing let's check out quiz 13. Okay, so this quiz is obviously a open-ended quiz. Okay, so the setting is this. Okay, I know you're not Bill Gates, you're not Mark Zuckerberg, but you could be thinking this. Okay, in your mind, you say, it's time to get real. Okay, and you decide this is enough college education. Okay, and I think Petbook is totally better than Facebook. And Petbook, it's a social net for the animal lovers. Hey, lots of us out there, lots of animal lovers out there. And so, hey, so Polly is here showing a design of Petbook. Okay, and this is Polly's cat. Okay, you've heard her meowing in the background of some of the in some of the videos. Okay. All right, now you being your own CTO on top of being also the CEO, CFO, CEO, hey, you know how startup is like, right? You do everything in a startup. And there's no hierarchy, everything is flat, okay? Try to structure your Petbook server network. Oops. Try to structure your Petbook server network such that, okay, you direct the pet page queries to the you direct the pet page queries so that the server load is balanced and the response time is low. Hey, very much like what DNS is trying to do, right? There's a DNS server network, and there's a certain way the query is forwarded, okay, and eventually gets the content the users are looking, the clients are looking for. All right. Good. Now I ask you, would you prefer modeling your service? So I'm asking you to architect the Petbook server network. Okay. Would you model your server network behind the HTTP architecture or SMTP architecture or the DNS architecture? Allow Polly to explain the differences between these two protocols' architecture. Okay. First, okay, so I see Jen Guy is already saying HTTP. Interesting. Okay, so HTTP's architecture very straightforward, right? So a client and a server, and it's flat. And this is SMTP, the receiving server, and there's a sending server, which is local to the sender of the email. So you kind of have you kind of have a local SMTP server. And this is the DNS's architecture. Okay. So you have a distributed database in 3 levels of hierarchy, storing the entries or storing information to find the entries eventually. And then you also have a local DNS server, okay, that's storing queries and potentially caching replies coming from the servers. Okay, so this local DNS server is acting on behalf of many local clients, sending queries and temporarily storing the replies to these queries. Okay, so let me try to abstract these 3 kinds of architectures. Okay, by okay, so before I do the abstraction, okay, so you see that the one architecture is more elaborated than the earlier one. So in SMTP, I kind of expand the client side, or hey, internet engineers expand the client side of the architecture, right? So you have 2 components at the client end. And between DNS and SMTP, right, you see the server end is also expanded. Okay, and so eventually in the DNS architecture, you see the architecture is expanded both at the client end and the server end. Okay, now let me abstract these 3 architectures. So the HTTP one is very straightforward, simple client, simple server. Connecting between one connection between client and server. In SMTP, elaborated client side, but still simple server side. But in C, you have elaborated client side and elaborated server side. All right. So this is what I meant by, okay, whether you would architect your pet-book server network based on the A model or B model or C model. Okay, so this is an open-end question. Therefore, oh, okay, team 4 is really fast. Okay, good for you. But hey, guys, find your teammates. You guys have 10 minutes to discuss. Okay, it's more important that you justify your choice. Okay, if you take A, why? If you take B, why? If you take C, why? If you take maybe starting with B and then later change to C, why? All right, so 10 minutes discussion, 1 minute to type things up. It's now 11:53. Let's see what you guys come up with. All right, and let's start counting time. Hey guys, and it's okay to use a hybrid of A and C as well. I think team 1 here is suggesting for the client end, I would prefer it simple like HTTP, but for the server end, I prefer it being more like the server side of DNS. I think that's what you meant, team 1. Okay, interesting. And you know what? Team 4's answer is also appealing, right? Because Team 4 is saying we just take C, DNS. Because you can think of the local server there in DNS as a cache for web pages that are often queried. And that will save some response time, definitely. And save the load to the system, okay? I think Team 4 totally makes sense. Yeah, and I see from team 10, 志祥. Yeah, so team 10 prefers just the HTTP model in the early time of the company. So at the beginning, there are not going to be much tractions. I see. So you prefer things that are simpler and therefore cost less and easier to maintain. Okay, very, very economical thinking. Okay, I think this is a good mindset starting a company, definitely. Okay, so we do have a couple more teams saying DNS, yeah, because it will be able to take more loads. I think this is from team 9 and 7. And a couple more teams saying that we prefer HTTP's model, the A model, because it's simpler. Yeah, anyone says the B model, something in between. Okay, so far we don't have the B model team. Okay, we have two more teams. Okay, finishing the debate. And I think there's also something going on the chat. Okay, the name in Indian water and the Greek city. You're playing Jeopardy, I see. All right, so hey, we have a few more teams. Say. Okay, so 11 says, I would take C because Petbook is going to grow bigger than Facebook. For the low, definitely. Okay, a distributed server network. DNS for Team 13 as well. Team A is also assuming that the network is going to grow bigger than Facebook. It's better to use DNS, I see. Yeah, because that architecture can definitely handle, of course, also low load. Okay. We think, and the illustration. Oh, interesting. Very interesting. So you kind of, you also have the design to divert the traffic, right? And it's a little bit like the top level domain server, right? With separating .com, .gov, .edu. And you kind of separate the traffic, the queries for dogs or cats and birds. So you come up also with the load balancing mechanism. Nice, very nice. And team 2 here, we think a multi-level cache server architecture is best suited. Content related to each other geographically. Very interesting. Okay, so the way you try to distribute the content is based on the geography, right? Very interesting, very interesting. So you're probably storing the pages of animals from Europe in the European top level server. And the pages in US are in the US top level page servers. Okay, so it's a different kind of load distribution mechanism. Makes sense, because chances higher that the European users look up European users' pages. Very interesting. Nice. Team 14. Oh, Team 14 begs to differ. SMTP. Judging from the growing demand, may not be capable, but I tend to make the most of the things. Unless I'm sure that using is going to be dead, I won't switch. Oh, okay, so Team 14 is taking a very experimental approach. So let's deploy something that's lower end and wait and see before switching. Okay, so very experimental approach. Love it, love it. So by the way, many people actually argue whether engineers are just experimental experimental scientists. Okay. Team 5, we find the HTTP model more suitable for the case because unlike a company like Facebook, we do not need to store as much data. Additionally, DNS is significantly more expensive, obviously, right? If you want to build the server network such as DNS, it's costly. So Team 5 again is having also the startup mindset as well. Over time, we may consider switching to SMTP DNS. Yeah, so progressively expand the architecture. I mean, if you start using, if you start from the A model, right, having just one server, I mean, it doesn't hurt, right? Adding 2 extra, 3 extra, or moving the server somewhere to other regions in the world later on. Okay, so this is something that we've seen earlier. And hey, Team 12, the beginning, we don't have a lot of resources HTTP, but we can change that to DNS when you grow bigger. Okay, good. And Team 15 also beg to differ. We would like to choose by using DNS. Same. The structure. Then, but hey, Clara, then I think you meant C, right? Because DNS is C. All right, good. Very good. So guys, you get the idea. So trying to decide the architecture for your application is also part of the design process. It really depends on what you're expecting. Okay. And very good to see that some of the teams actually devise also, in case you're choosing DNS, right? There's a load balancing mechanism you might also want to consider. Okay, nice. And let's see. Okay, so I guess that's all. That's all. And it's already 12:09, and you know what? I will say goodbye now, and I will see you next week. And we'll continue to talk about DNS. And we are not yet done talking about these mappings, how they look like in the database, and how the queries for the mapping look like, and how the replies containing the mappings would look like. And that's something that will come up next Tuesday. I'll see you next week. Bye. Okay. Bye, guys. Um, 10 minutes later, there's gonna be a testing session. So if you guys want to test the camera setting and network setting, come, but 10 minutes later. So that's gonna be starting from 12:20. Okay, I'm gonna close the stream so that you guys can start the test run earlier.